All right. So when we had wrapped up class on Friday, we had just finished talking about the output stage of our common emitter amplifier and found out that it contributed a zero at omega is equal to zero and a pole at 1 over RLC out. So what we're going to look at now is the input stage of our system. So I want to scroll back up here so that we can kind of see what's going on here. Okay. So effectively what we're going to have is the network to the left of that dashed line, but we can't forget that that node Vx is connected to the base of our amplifier stage. And so we are going to essentially have something that looks like this. So for our input stage, we've got our input signal Vn in series with some signal resistance R sig in series with our input capacitance, which has an impedance of 1 over SCN. Our resistor R1 and R2 are going to look like they are in parallel since VCC looks like an AC ground. This is effectively node X. So I'm going to put my voltage drop across that guy. But then we also have to take into account the impedance looking in to the base of our amplifier stage, which I'm going to represent here as an impedance that I'm going to call Zn prime. So Zn prime is just the impedance seen looking into the base terminal. And so using the relationships that I developed in that handout that I posted on the files section or whatever, where I got that voltage gain from, the input impedance of a common emitter amplifier, or the impedance seen looking into the base terminal of a common emitter amplifier, is going to look something like this. So we'd have R pi times ZE times 1 plus GM R naught plus R naught plus ZC times R pi plus ZE, all divided by R naught plus ZE plus ZC. Now, this isn't what we are going to use because this is a terrifyingly complex thing, right? So having a ZC and a ZE in the numerator and then having those in the denominators, the math just gets utterly ridiculous incredibly quickly. So what I did is I approximated this by the relationship R pi plus 1 plus beta ZE. This relationship, for what it's worth, isn't something that I pulled out of thin air. This is nothing more than Zn prime with the early effects neglected. And I chose to represent it here, or in this way, because it's much easier to deal with. Hopefully, algebraically, it should be very obvious that the approximation here is going to be much easier to deal with than the large thing. So like we did in class on Friday, let's see what impact this has as a function of error, okay? So, I have it down here in the middle. So what I have as ZN1 is the full expression, where we wound up getting 3.534 kiloohms at the particular frequency that I was looking at. And then ZN2 wound up being 3.571 kiloohms, introducing an error of 1% at this frequency, which isn't particularly bad. I also, just to see how things would shake out, played around with making it an even easier approximation to deal with by just throwing away the R pi, and notice that that gave us 0.971 kiloohms compared to 3.5 kiloohms. To me, that was way too much error to consider to be acceptable. This next bit afterwards, where I have AX1 and AX2, so that is me just evaluating the transfer function of that stage of the amplifier, literally just treating it as if it were a voltage divider network, because that's exactly what it is. The one on the top is using the impedance ZN1. The one on the bottom is using ZN2, which is our approximation where we are neglecting early effects. And notice that they give us literally the exact same result. So while there's a 1% error in the impedance as part of the larger system, it actually washes out. What I have over here on the right-hand side, A1, is effectively me just treating that Zn as if it were an open circuit, kind of like we had a MOSFET, just to see how good of an approximation that would be. And it was actually pretty decent, just literally ignoring it completely, but the math wasn't too difficult with the approximation, so I went ahead and did it that way. All right. So just wanted to explain, where I'm introducing error and all that kind of good stuff. So finding Vx over Vn is nothing more than the application of voltage division, right? So we would be finding the ratio of R1 in parallel with R2 in parallel with Vn prime divided by R sig plus 1 over SCN plus R1 in parallel with R2 in parallel with Vn prime. Now I'm skipping a ton of math here because we're a little bit behind where I wanted to be. But 3, I think, whiteboards full of algebra got me this result. So this looks like S times R1 in parallel with R2 times Cn multiplied by R pi plus 1 plus beta Re plus S R pi Re Ce, close that bracket, all divided by a second order polynomial. Sorry, this should be A times S squared plus B times S plus C, where, and I'm just going to give you fair warning, these coefficients are gross. A is Re times R sig times R pi plus R1 in parallel with R2 plus R pi times R1 in parallel with R2. B, I found to be Re times R pi plus R1 in parallel with R2 times CE plus open brackets R sig times R pi plus R1 in parallel with R2 plus 1 plus beta RE plus R1 in parallel with R2 times R pi plus 1 plus beta RE. And all of that was multiplied by Cn, or everything in the brackets was multiplied by Cn. And then lastly, that coefficient C came out to be R pi plus R1 in parallel with R2 plus 1 plus beta RE. So it wound up looking like a second order polynomial in the denominator by using that approximation, right? So we can see pretty easily here that we have two poles from our second order polynomial in the denominator, two zeros from our two discrete first order relationships in the numerator. Before I gave up on the math by not making this assumption, it was looking like it was going to be like 4 or 5 zeros and poles. And so I was just like, that's just too gross for me. Just ran out of mental steam to sort that stuff out. Okay. So from this stuff here, we have a zero. So let's call this omega zn1 at 0. A second 0, so that'll be omega zn2 at negative R pi plus 1 plus beta RE all over R pi times RE times CE. And then our poles are just going to come straight from the quadratic formula. So negative B, actually, should be up here, plus the square root of B squared minus 4AC all over 2A and omega Pn2 is negative B minus the square root of B squared minus 4AC all over 2A. So we wound up with this approach where we've made multiple approximations to make things easier. I believe a grand total of 5 zeros and 5 poles in our transfer function. So that's a lot of work. And I would argue that we don't always care about what's going on in the low frequency response. Sometimes we just care about where our cutoff frequency is. So what I want to introduce to you guys now is what's called the short circuit time constant method. And it's what we can use to approximate where our midband begins. So let me change the color. Hold on. All right. So let's write this down. All right, so in the short circuit time constant approximation, let me explain effectively what we're going to be doing. So we are going to say that omega low, which is our low frequency cutoff, should approximately be equal to the sum from I is equal to 1 to n of the inverse of the time constants associated with each capacitor in our network. Where, so this would be like 1 over R1 times C1, where C2 through Cn are assumed to be short circuits. And then we would add to that 1 over R2 C2, where C1, C3, all the way out to C sub n are assumed to be shorts, and so on and so forth. So effectively, we just find the equivalent resistance connected to each capacitor, while all of the other capacitors appear as short circuits. So this is our approximation method, and I mentioned this in class on Friday, but it's only valid whenever we have a dominant pole, which means that effectively we need our highest frequency pole to occur at least 10 times the frequency of our nearest other pole. Otherwise, this doesn't work at all. All right, so let's look at our first time constant. Okay, so we're going to start with the resistance seen by our Cn capacitor. So I'm going to draw a picture here. So I'm connecting my signal resistance to ground because we're effectively finding a Thevenin equivalent voltage. So I need to be looking at a dead network. So my input signal is turned off. Okay. Here are the terminals where my capacitor was. These are the ones that we're looking into. So I'm going to call this RCN. Because we're looking at a dead network, VCC is off, so we're going to see R1 in parallel with R2 down here. And then over here, we would have our transistor amplifier. Now, because CE is treated as a short circuit, the emitter terminal is grounded out, right? So CE is bypassing that resistance R because we're treating it as a short circuit. And then up here, I'm going to see RC in parallel with RL. Just to make sure we're all on the same page here, let's go back to my original circuit diagram. So when C out is a short circuit, RC is connected between the collector node and AC ground, and RL is connected between the collector node and AC ground. So those two guys appear like they are directly in parallel, which is why I drew it that way. And Coming back down to this thing. We effectively just need to know what this resistance looking in is going to be. So what should the resistance looking in to the base of a common emitter amplifier without degeneration be? Just R pi, absolutely right. So from this, RCN is just going to be R sig in series with R pi in parallel with R1 in parallel with R2. And tau 1, for lack of a better word, is just R Cn times Cn. So any questions about that guy? Fantastic question. So R sig isn't in parallel because it doesn't share this node, right? So how I came up with that is if I tie all these grounds together, I effectively have something that looks like this. So here's my terminals of my capacitor. Here's R sig. I'm going to put ground over here. And then down here I have R1 in parallel with R pi. Parallel. That's not a pi, right? So connecting those two nodes together, looking in through those terminals, it looks like R sig is in series with it. Yeah. So it's just looking at grounds without literally thinking about, well, all of the grounds are connected together makes it less obvious. But once we treat it as that's just a node, it seems a little bit easier to understand. All right. Any other questions about this guy before we go on? Yes, Nathaniel. The top node BCC is very much ground. So, great question. So let's draw a small signal model really quickly and make sure that they don't. Okay. So this is just looking into the base terminal of our amplifier, right? So here's our base terminal. Here's R pi dBe. Our emitter is at ground. Here's GM VBE in parallel with R naught. Here's our collector node. And then between the collector and our AC ground, we have RC in parallel with RL. So can we agree that this is what we would see small signal looking into the base? Okay. So if I put a test voltage source here, the resistance looking into the base is just the ratio of Vx over Ix, right? So, I'm not worried about that part right there. I'm just looking in to here. Yeah. Because whatever I see looking into here is in parallel with R1 and R2. Okay. So what's the resistance seen looking in? It's just R pi. Doesn't matter what RC and RL are doing over there. IX only sees a resistance R pi on its path to ground. Yeah. So it'll crop up in some places, but it won't crop up particularly here. If we had the generation, it very much would. Right? So just to be really clear here, if we had the generation effects to be present, everywhere that we see this Z, we would just replace it with RE. And everywhere we see this ZC, we would replace it with RC in parallel with R. But the beauty of the short circuit time constant method is that CE is showing up like a short circuit when we're doing this particular analysis, which makes the overall majority of this verifying looking thing away. So let's do another easy one. This will be the resistance seen by the out. So here's R sig. R1 in parallel with R2 connected to the base of my transistor. My bypass capacitor CE is still sorting out that resistance RE, so it's not showing up anywhere. Here's RC. Here's RL. And we're trying to find this resistance RC out. So I would argue, let me put something here. So this is the resistance that we see looking down into the collector terminal of the amplifier. So to me, RC out is going to look like RL, so that's the resistance that we have on the right-hand side, plus RC in parallel with that resistance R down, where I have RL plus that resistance because we have effectively the exact same situation that we had previously. We have some resistance between the left-hand terminal and ground and some resistance between the right-hand terminal of the capacitor and ground. And those resistances appear as if they're in series, if we treat ground as a common node connecting. Okay. So what is the resistance seen looking down into the collector of a common emitter amplifier with no degeneration? Yes or not? Absolutely right. So RL plus R naught in parallel with RC. And then we could call tau 2 simply RC out times C out. So those two are the easy ones. If we want to find the resistance seen by capacitance CE, this is where things get a little bit more difficult. So I'm going to draw my picture again. So here's R sig. R1 in parallel with R2. Here's RE. Here's RC in parallel with RL. And this is the resistance that we're looking for. So just so that we're kind of approaching this in a similar way to what we have done before. To me, this looks like the resistance RC, which is what we see at the emitter node looking down, in parallel with whatever we're going to see looking into the emitter node looking up. Okay. Now, I posit that we have actually seen this before. We haven't seen this in a couple of months, so it's not going to be something that easy. So it'll be Rn for a common base amplifier with a base resistance of R sig in parallel with R1 in parallel with R2, right? What did you say it was, Sam? Let me see if I can wrap my head around it. Yeah, so for a common collector, we would apply our input signal. I mean, I think that's also correct, but it's the same, literally the same. We covered common base first before we covered common collector, which is why it looks like that to me, because I'm almost positive I derived this. In fact, I brought my notes just in case you guys tried to make me do it. But I think that the resistance seen looking up here would be R pi plus RB, where I'm treating RB as R sig in parallel with R1 in parallel with R2. Times R naught plus RC, where in this case, that's RC in parallel with RL, all divided by R pi plus 1 plus beta R naught plus RB. That would be R sig in parallel with R1 in parallel with R2 plus RC in parallel with RL, like so. And then RCE is just RE in parallel with R up, and tau 3 would simply be RCE, excuse me, times CE. So to complete this method, since we only have the 3 capacitances, we found the 3 resistances seen by each capacitance. We would simply take the inverse of each time constant, add them together, and that would give us an approximation for where our midband begins. Yes. There's nothing stopping us from putting more capacitors. That being said, there's not any practical reason. So, like, the capacitor Cn is providing AC coupling of our input signal to our amplifier. So, I mean, it serves a purpose, right? The capacitor CE is a bypass capacitor so that we get the benefits of emitter degeneration in our DC circuit without having to decrease our midband gain for our AC circuit. And then the capacitance C out is effectively decoupling our DC signal from our load resistor so that we only see the AC signal on that. Any other capacitor that we added, like I don't know what its purpose would be. We can always just put them in there willy-nilly and it'll screw with the frequency response of our system, but I don't really see the point of any others. Yeah. All right. So we've discussed our low frequency response by direct analysis with some important simplifications made just to make the math less horrifying, still horrifying, but less horrifying. We have this method for estimating where our low frequency response ends effectively under the constraint that one of these poles is going to be dominant. So effectively, if one of them is dominant, then one of these time constants is going to be much larger than the others, and it's the one that's going to set our frequency response. So let's look now at high frequency response of a common emitter amplifier. And in some ways, this is actually going to be easier. We're not going to have to make any approximations whatsoever. We can get a direct result. But in other ways, it's going to be a bit of a pain in the butt, which, kind of makes sense because you're dealing with a class with me. All right, so my goal to cover the direct analysis for this today. So we are going to analyze the circuit, making literally no assumptions about anything. And then on Wednesday's class, I'm going to introduce what's called the Miller method that will allow us to split impedances up. So that'll be one way that we can approximate the response of this circuit. And then we're also going to introduce the method of open circuit time constants, which is how you can approximate, or you can make an approximation of where the high frequency response is going to be good. All right, so at high frequencies, our fully biased common emitter amplifier is going to look something like this. So what I'm going to do is I'm going to draw our original circuit with all of my coupling and bypass capacitors shorted out. And then on top of that circuit, I'm going to superimpose my internal capacitances so we can kind of see what's going on. Okay. So here's VCC. Here's my resistor R1. Here's my resistor R2. Because Cn is a short circuit, I'm just going to have my signal resistance directly connected to that node. Here's my input voltage Vin. Because CE is a short circuit, I'm just going to have a short circuit path directly from my emitter to ground, which makes our life much easier. Up here, I'm going to have VCC. And then this is going to be RC in parallel with RL, because when C out is a short circuit, we see both of resistor RC between our collector node and AC ground, and RL between our collector node and AC ground. So now let's superimpose some capacitances, right? So we know that we should have a capacitance between the base and the emitter. So this is our capacitance C pi. We should have a capacitance between the base and the collector. This is our capacitance C mu. And then we should have a capacitance seen between our collector and ground. Which is the capacitance CCS. Now, CCS, I mentioned in class, only appears when we are dealing with an integrated circuit thing. I'm going to leave it in. We can always take it out if we need it. All right. So we're going to throw the kitchen sink at this guy. I'm going to start with just drawing the small signal model for this whole thing. So let's put Vn over here on the left. Here's R1 in parallel with R2. Here's my base node. Here's R pi. Directly in parallel with R pi, I should have an impedance of 1 over S C pi. So that's the capacitance that's between the collector and the emitter. I chose to represent it as between, excuse me, the base and the emitter because my emitter is at ground. I just drew it like that up above, but now I'm putting it explicitly in parallel. Here's my grounded out emitter terminal. Here's GM VBE in parallel with R naught. Here's my collector terminal. So between my collector and ground, I have a resistance of RC in parallel with RL. I also have an impedance of 1 over S CS. Here's my output voltage node, which I did not remember to draw up here. So I apologize for that. Output still just taken at the collector node now. And then I cannot forget the biggest pain in the butt we're going to have for a little while. This capacitor, 1 over SC mu, that's placed between our base node and our collector node. So we can make a couple of observations about this thing to make our life easier. And the observations that I'm going to make here and the simplifications that I'm going to make actually means the analysis for the high frequency response of a common source amplifier, or the MOSFET version, and the high frequency response of this guy are going to be literally identical by the way that I'm breaking things up. The only relationship that's going to change is what value some of the resistances have. Okay? So the first thing that I'm going to do is I'm going to notice that the resistance R naught is between the output node and ground. The resistance RC in parallel with RL is also between the output node and ground. So I'm going to lump all of those guys together and treat them as a single resistance, which I'm going to call R naught prime. Okay. So I'm just tying all of this together. I'm going to call that R naught prime. Now, another thing that I'm going to do is I am going to find the Thevenin equivalent circuit of everything to the left of this dashed red line. so that I can replace that entire network with just a voltage source in series with a resistor, because it's gonna make it easier to deal with. So let's sort that bit out really quickly, okay? So we have a voltage VN. Here's R sig. Here's R1 in parallel with R2. Here's R pi, and I'm just going to tie those three grounds together down here. And I'm going to call this voltage VThev. So using voltage division, VThev is nothing more than R pi in parallel with R1 in parallel with R2 over R sig plus R pi in parallel with R1 in parallel with R2 times Vn. We okay with that? Simple voltage division. R thev is going to be found by looking in to the terminals on the right. So here I've got R sig. It's in parallel with R1 and R2 now because we turn the input voltage off. We need to be looking at a dead network. R1 in parallel with R2. R pi. Look in. And it's pretty obvious to see that all of those resistances are just in series. Or excuse me, just in parallel. So R thev will be equal to R pi in parallel with R sig in parallel with R1 in parallel with R2. Are we all okay with that? I'm going to call this R sig prime. And now I'm going to use these simplifications, not assuming anything away. We're just drawing it in a form that makes it less of a pain in the ass to analyze. So I'm going to integrate these simplifications, and our small signal model would now look something like this. So here's VThev. Here's R sig prime. Here's my impedance of 1 over S C pi. My voltage drop VBE. VM, VBE, R naught prime. One over S C CS. Because the bottom node of this is at ground, I'm just going to tie it together over here. Here's our output node. And lastly, I throw that C mu capacitance in the middle. 1 over S C mu. So this is still daunting, but it's not overwhelmingly so. Okay? So the last thing that I'm gonna do is I'm just gonna call this voltage with respect to ground Vx. And the voltage at this node with respect to ground Vy. I understand that V out is literally the exact same thing as Vy, but it's less for me to have to write down over and over and over again. All right, so first thing that we're going to do in our analysis here is to just apply Kirchhoff's current law at node Y. So at node Y, I'm going to have a current flowing through the impedance 1 over SCU to the left. I'm going to have a current flowing down because of the dependent source. I'm going to have a current flowing through my resistance R naught. And I'm also going to have a current flowing through my capacitance CCS. So to me, starting with the current flowing through my capacitor to the left, that's going to look like S C mu times Vy minus Vx. Now I have my current flowing down through the dependent source. So that's going to be GM VBE. But what's VBE now? Vx. Plus Vy over R naught prime plus SCCS times Vy is equal to 0. I'm going to lump all of my Vy terms on one side of the equal sign, all of my Vx terms on the other side of the equal sign. And so what I wind up getting is Vy times SC mu plus 1 over R naught prime plus SCCS is equal to Vx times SC mu minus GM. And from this, I can say that Vx is 1 over R naught prime plus S times C mu plus C CS, all divided by negative GM plus S C mu times Vy. My algebra looks okay. All right. So what we're going to do now is we're going to apply KCL at node X. So let's look up here. So I could really just have 3 currents, right? I'll have a current flowing to the left through R6 prime. I'll have a current flowing down through my capacitance C5, and I'll have a current flowing to the right through my capacitance CV. So just using good old Ohm's law to express all of those capacitors and all of those currents in terms of our nodal voltages, we wind up getting S C mu times Vx minus Vy plus Vx minus Vthev over R sig prime plus S C pi Vx is equal to 0. And now I'm just going to rearrange this guy such that all of my Vx and Vy terms are on the left-hand side of the equal sign, and all of my Vthev terms on the right-hand side of the equal sign. So that's going to look like Vx times Not read that one. S C mu plus 1 over r sig prime plus S C pi minus S C mu dy is equal to V fev over r sig prime. And I can now substitute in my relationship for Vx from my KCl at node y into this equation. And what I wind up getting is this guy. So I'm going to have Vy times 1 over R naught prime plus S times C mu plus CCS divided by negative GM plus S C mu times 1 over R sig prime plus S C mu plus C pi minus S C mu is equal to V fev over R sig prime. All right, so now I've got roughly half a page to 2/3 of a page of algebra that I'm going to skip because it's boring for you guys and it doesn't actually provide any information about the behavior. It's just math that's what it's got. I'll post the derivation for those of you who want to see me suffer through the algebra, but I'm not going to make you do it in real time. So what we're going to wind up seeing is that V out, which is nothing more than Vy, divided by V fev comes out to be, let me give myself a huge thing here. S squared times R naught prime times R sig prime times C mu C pi plus C mu CCS plus CCS C pi plus, is it going to confuse you guys too much if I do this next coefficient underneath? Because it's going to be gross. Actually, you know what? Let me do this in a different way. Yep, A squared or AS squared plus BS plus C. Where A is equal to that thing. B is equal to, this is going to be large, R sig prime C mu plus C pi plus R naught prime C mu plus CCS plus GM R naught prime R sig prime C mu. And I'll put C over here. It's 1. So that's our denominator. Our numerator is just negative GM plus S C mu times R naught prime. So very obviously, the second order polynomial is going to wind up giving us two poles just using the quadratic equation, right? Negative b plus or minus b squared minus 4ac all over 2s. Okay. Nothing hard there. What we got to figure out now is what's going on with our numerator, because at no point in any of this did we pull out our midband gain. Ryder, you got a question? Which parentheses? Oh, let me draw that C in front of C mu more like a C. Sorry. Yeah, capital C's and opening parentheses are getting me in trouble. I apologize for my penmanship. Let me know when I'm good to scroll down so we can start playing around with this numerator. All right. So our denominator is giving us our poles. That's just the quadratic equation. I'll write it down in a minute, but it's the same exact thing that we saw earlier. Okay. So looking at our numerator, we have negative GM plus S C mu times R naught prime. So I'm just going to distribute that R naught prime. So that's going to be negative GM R naught prime plus S R naught prime times C mu. And now recall from up here that R naught prime is just those three resistances in parallel. I'm going to continue to treat RC in parallel. Actually, I'm going to flip it up. I'm going to treat R naught in parallel with RC as a single resistance, and then RL as a discrete resistance, because I know that I'm looking for a GM times R naught in parallel with RC. So this would look like negative GM R naught in parallel with RC in parallel with RL plus S R naught in parallel with RC in parallel with RL times C mu. So I would have negative GM R naught in parallel with RC times RL. Let me make sure that the RC looks like an RC so I don't accidentally mansplain algebra again. All right, are we okay to this point? Right, so I'm going to wind up finding a pole, but I'm also going to pull out my midband gain from this, because we know that our high frequency response should be able to express in the form of midband gain times high frequency zeros over high frequency poles. So I'm going to go ahead and pull out that midband gain here. We're using the exact same midband gain as we did in the low frequency response because we have to. They should be literally the exact same thing. So that's just going to be negative GM R naught in parallel with RC. So when I pull that out, I'm going to be left with RL divided by R naught in parallel with RC plus RL. I'm going to put plus here. And so I'm going to divide this SCU term by negative GM R naught in parallel with RC. And then I'm going to multiply by that ratio of resistances. Oh, stop scrolling on my screen. I'm going to put those brackets there so it makes it easier to sort what's going on. And then close these here. All right, so looking at this guy, I can see that on my right-hand term, I have an R naught in parallel with RC in the numerator and an R naught in parallel with RC in the denominator. So those guys are going to cancel each other out. So that is going to give me negative GM R naught in parallel with RC times. Actually, let me do one other thing here really quickly. I'm not going to make you guys erase anything. I'm going to multiply both sides through by negative GM over negative GM, just to get rid of a negative GM in that denominator, and you'll see why in a moment. So this is going to look like negative GM RL all over R naught in parallel with RC plus RL. Plus SRL CU divided by R naught in parallel with RC plus RL. And this is the term that I'm going to use to get my zero. Okay. Yes. I'm not, could you come point out what you're talking about? Yeah. Okay, I see what you're talking about. And that's all changed since then. Okay, thank you for that. Nope, 100% right. It wasn't going to cancel the negative GM outside at all. It just means that what I have written down for where my zero occurs messes things up. Let me so effectively, the reason why I'm trying to get rid of that negative GM is so that I have the same denominator on both of these, because when I algebraically organize things to solve for when this is equal to zero, those guys are going to wind up canceling each other out. So let me but I can't bring in the negative GM from out front because that's part of my midband gain. So that needs to be on the outside there. So if I multiply the right one by let's okay, so let's erase this. We'll put a pin in it. We'll figure that out in a second. Okay. So yes, ma'am. Okay, yeah, 100% correct. Let's do that. Thank you for that. So just multiplying that left-hand term, we would have negative GM RL over negative GM times RL plus R naught in parallel with RC. Close that out. Plus SC mu RL over negative GM times that same RL plus R naught plus RC. Which is, and just move the GM in the numerator. Yeah, I'm just bad at multiplying is apparently what it is. Because either way I did it originally, I made a mistake, whether it was not putting it in the denominator or I should have put one in the numerator. This is gonna work out totally fine. I'm gonna leave it at it. But you're 100% right. I could have, that would have just put a negative GM squared down here. So I just made an asinine algebraic error to begin with. Yeah. I was definitely wrong to start with. But this form will do exactly what I want, and it's what I meant because looking at it, I know it's going to give me the answer that I was looking for. So, thank you, Hannah, for showing me how to do it correctly. All right, so our zero is going to occur whenever that big expression in the brackets is literally equal to zero, right? We would just solve for the f value that makes that happen. So we would have S times C mu RL divided by negative GM times RL plus R naught in parallel with RC is equal to negative GM RL divided by negative GM RL plus R naught in parallel with RC. And since our denominator is the same, they cancel. So from this, we would see that S would be negative GM RL divided by RL C mu. The RLs cancel. And from this, our high frequency zero, we're only going to have the one, could just be GM over C mu. Yes. Thank you. Yes. So I was worried about that actually because I know that this was supposed to have a positive zero, and that's the next thing that I want to talk about. So thank you for catching that. You're 100% correct. So our zero here is a positive. right? Every other zero that we've had has been either literally zero or negative. So this is not in and of itself a problematic thing. However, what having a zero in the right-hand plane tells us, and I understand I'm 2 minutes over, so I'll shut up in literally just a moment. What having a zero in the right-hand plane tells us is that if we connect this circuit as part of a feedback circuit, this is going to give us potential instability because this is what's going to cause negative feedback to look like positive feedback at high frequencies. So we're going to have to do something to correct this if we want to use it in a feedback circuit. If you look back at I can do this really, really quickly. Open the file. Close that. Trying to do a little faster. There we go. All right, so just very, very, very quickly here. This capacitor right here is what's called a compensation capacitor. And its job is to effectively pull that zero back over to the left-hand plane so that this thing is stable at high frequencies. Okay. So that'll be something that you're going to learn about in the integrated circuits class. I don't know that we'll have time to get to it here, but there is a way to effectively use components like capacitors and a technique called pole splitting to force our frequency response to behave the way that we want and to ensure stability. So really all this guy is doing is just moving that frequency response over so that we make sure that our gain actually falls to 0 dB or less before we get 360 degrees of phase inversion, which is going to make our negative feedback look like positive. So anyway, all right, done.